Welcome and good morning, everybody. I'm very, very happy to present all the international expert speakers who have said yes for the fourth AI rendezvous in few minutes. Exactly, we will listen to leading international experts from academia and industry to examine concrete application of AI. During plenary lectures in few minutes and this afternoon, so please stay with us all the day long to listen to high-level roundtable discussion. So now I would like to introduce Claire Rossi, Director of the UTC for an introduction to this fourth edition. Please, you can applaud her.
Dear colleague, dear partner, dear student, I'm very pleased to welcome you here at UTC and also for those that are joining online today and say hello to the partner of Sunrise Alliance. So the massive present of today is reflecting something essential. Artificial intelligence is not only a technological topic, but is now a collective, international and deeply interdisciplinary challenge. So for those of you that are not very familiar with UTC, let me briefly introduce our institution. So UTC is both an university and engineering school, and it's built on a strong conviction. Technology must be developed in close connection with human and societal challenge. Our model is based on interdisciplinary education, combining engineering and human science, project-based learning, close connected with real-world challenges, and a strong partnership with industry. And we train engineer, master, and PhD students able to understand the complexity, work across discipline, and transform knowledge into innovation. And this positioning is particularly relevant for the context of artificial intelligence. So here, this is not a new topic. It's part of our scientific foundation. We have a long-standing expertise through our laboratory, Destercke. It's a laboratory internationally recognized in artificial intelligence, control, and data science, and it's now rapidly expanding across the other laboratories in many domains, including process, formulation, and nutrition, which is precisely the focus of today's discussion. So now we are developing since few years new initiatives such as the Share Safety EA that focus on key challenges like reliability, robustness, trust in EA system. And I think that Sébastien will say a few words after on that. I'm looking where is that? Okay, sorry. Now we are entering in a new phase of acceleration. UTC is part of the post-Gen AI Paris cluster led by Sorbonne University that was awarded by 35 million euros to develop cutting-edge research and training in artificial intelligence. And this cluster is belonging to the 9 national cluster for global ambition and is positioning UTC as a major national and European dynamic structure for the next generation of artificial intelligence ecosystem. And we are going even further. We are currently launching new interdisciplinary research center dedicated to artificial intelligence and technological system. And this ambition is to bring together AI, engineering science, domain expertise from health to energy to industrial system to address complex and real-world challenges. We are believing that in the future, all the application and the use of artificial intelligence will not build in silo, and it should be integrated at the intersection of discipline, application, and responsibility. And the impact of artificial intelligence depends on its ability to be integrated in real industrial environment, in real data, real constraint, and real use case. So, as you say, that at UTC we have a strong culture of partnership, and we are working closely with company through industrial share, joint laboratory, collaborative research and innovating project. And dear partner, we are at your disposal to work with you on topics that matter to you. They can be strategic, exploratory, or directly linked to your industrial challenge. And because we are strongly believe that innovation emerges from dialogue, trust, and long-term collaboration, is the reason of this kind of events. We are all together here to discuss and think of the future of the application of artificial intelligence. So now it's time to start the day. Again, I would like to warmly thank all the speakers, the partner, and you to be there today. And I wish you a very fruitful day, inspiriting day with all of discussion, and we hope that is going to build new collaboration. So thank you a lot and have a pleasant day.
Thank you very much, Claire Rossi, Director of the UTC. Thank you. Exactly. And now a few words from Sébastien Destercke. Please welcome her with your applause, holder of the chair Safe AA. Merci. À mes côtés, ça te va?
Welcome everyone. I know you will have opportunity to thank the people that have organized the event, but I like always to start my interventions by thanking all the people that have participated to the organization. So would be Claire, Fadi, Audrey, Miriam, and also I don't see her because she's probably busy organizing the logistic, but Audrey that you've seen entering the building is there. So if you can give them a round of applause because they always do an amazing job. Okay, so I've been given the heavy burden because Sylvie Lemonnier is not there, so she has given me the task to present the foundations. So the chair I'm currently directing is founded by the foundations and some of its industrial partners. So Prasteria, Workday, that you can see there. So you don't know them because Prasteria mainly works in computer science, as a society that helps other industries. Workday works in human resources, but these are the partners that have founded the chair. That is the initiative of this event. And this is very nice to see that this event has taken up as a reason so that now it's part of UTC, and even larger part of Sorbonne, and so part of the Sunrise Alliance. So this is really now a quite international initiative. So this is very nice to see. So the foundations is the very spirit of the foundations is to put together students, industrial partners, academic partners, researchers, engineers, to build up some innovations. And so this chair is part of it, but of course the foundations also found student projects, also found, let me think about it, so also found student project, I've seen it, also found training formations, and plenty of things, expertise, as Claire said. So if you want to patron some of the events done by the foundations and be part of these events, then you can get in touch either with Claire, Frédéric, also Fadi, but also Sylvie Lemonnier, well, whoever you want. But you could patron, for example, another chair on innovation on formulations or innovation in process. Okay, so I'm very happy to see this interdisciplinary work taken up. And now I will present you a bit of what we do in this Safe AI chair. And I focused on some of the work that may directly interest you. We do other things. I may talk about it during coffee breaks if you want, but I wanted to put a focus on various things we have founded with this chair. Mostly are not from the computer science laboratory because you don't want to see computer science stuff. You want to see applications of computer science stuff. So things we have done, for example, with the mechanic lab is generation of new materials and polycrystalline new materials. But you could think of applying the same kind of things that Bing-Yang has done in formulations, in chemical products, in discovery of new things, new components, and so on. We also do, and this is mainly in the biomechanic lab, AI-assisted simulations and digital twins. And here I have two examples. So on the left is capsules that you put in the blood, and this is AI is there to speed up the numerical simulations and to make them as faithful as possible to our physical knowledge of the process. You have also a digital twin of a muscle here. The idea is to help people with aging muscles or with problems to get better care. My own specialty is in uncertainty quantifications. So here you see a problem of detecting defaults in hydrogen vessels. But I guess if you work in process in general, if you work in formulations in general, defaults are something that you're interested in. So this is part of what we do. And okay, here is the only focus because I like a lot that work done by a postdoc that is in Paris, not in Sorbonne, he's in Polytechnique, but he helped us to put uncertainty bounds around the prediction of a functional output. So this functional output here is the results of differential equations used in nuclear fusion. So the idea is to better control nuclear fusion, but I guess that you can think of process where the output, the thing you want to predict, is a function of something, is a continuous variable. So I'm done here. I've probably overstepped my time, but okay. Yeah. And I wish you all, so that's the last time you will hear from me, probably, because I'm not the star of this event. The people doing formulation and process are. And I wish you a happy and fruitful day.
Thank you very much, Sébastien Destercke. Merci. So let's start with our first great speaker. Please welcome Professor Georges Nychas. Please, you can upload her. Thank you. Him. Georges Nychas from the Agricultural University of Athens. He is a very, very emeritus professor, among the most influential researchers. He has published hundreds of articles. He is notably chairman of the Food Safety Working Group, an European platform, Food for Life. If you have any question after the speak, you will be able to ask your questions here in the room and in the networks. We can go.
Okay. Okay. Thank you very much for this.
So I'm also usually the technician in this kind of events, but here, Serge is there. So.
It's okay now. Thank you.
Okay, thank you very much for this nice introduction. I would like to thank the committee for inviting me in this very important conference. I have to admit that I'm not expert in this, so please forgive me if I don't pass the message that I talk about it. And this is part of the Food Guard project, a European project that we try to save the food, to minimize the food waste and food loss. So the title of my presentation is Meta Food Industry, from conventional control to automation to both humanization. And the structure of my talk, Fadi told me that I can talk the next 45 hours, but okay, I will do that in 45 minutes. Scrutinize what I have to say. And the structure is from food industry 1 to 4, current food safety system, because this is very important, and preventing rather responding. This is what we are doing in Food Guard project, and some thoughts about driving towards Industry 5. And let's go to first part, which is evolution of food industry. Just to remind you that Industry 1 was mainly on mechanization. Industry 2 was on mass production. Industry 3 was related to automation and computing. And Industry 4, smart factories. We have a lot of invest there. So we will find out what's going to happen in Industry 5. And let's talk about how is the transition from 3 to 4. You can see that from mass production, we have smart manufacturing, we have precision in agriculture, we have hydroponics, the introduction of Internet of Things, and pre-chain horticulture. Sorry. So let's move to the current state. And of course, food quality is something that we as consumers, we are take care, but mainly we are take care about the safety. The authorities, from every country, they care about the food safety. The consumers take care about the food safety. And let's say that we have 3 regions, Europe, China, Asia, and United States. So these are the difference between these areas, which also they have some similarities. For example, the European approach is to food safety aims at providing the highest level. It's very important for the European authorities to have the highest level of public health. In EU, risk assessment is science-based and centralized in the European Food Safety Authority, dominated by European Food Safety Authority. In USA, the approach is, because they have numerous federal, state, and local offices, there is a kind of dispute the last 3 years. Some of them, they want to centralize as happened in the European Union, but some others, they want to have these authorities in every single state. And the Chinese, they try to mix both of them. It's a huge country, 1.5 billion people, and with states, they call province, and they try to mix these systems. This is the Bible for European community related with food. This is the well-known law legislation 2073 of 2005. There is some updates even now. When the scientists discover something, there is an update on this legislation. And this is the European, the American one. They are jealous from Europe. So the last 5 years, actually they start in 2015, 2016. They have a Food Safety Modernization Act, which is more active the last 3-4 years. And the Chinese, they have different, as I mentioned, there are different places, different provinces. They try very hard to copy and to centralize not only inside the province, but to have something central from the central government. So they try to mimic a little bit the USA and Europe. So no matter where are you, being a food industry, the process that is followed now, it's very simple. It's based on the end product. So we have any product from farm to fork process. Usually the industry take a product, they send it outside to outsources for analysis. If some of them big companies, of course, they have internal laboratories. So they are waiting, give you for total viable count, which is the one of the legislation in the European Union, takes about 48 hours. So if you are looking for salmonella, it takes about a week. So you can imagine that this is not feasible because you want, especially when you have animal origin food like meat and fish, and you need to export that immediately. You don't want to wait after 48 hours to give okay in order to travel in another country. So this is, as you understand, is a problem, but this is the current food safety assessment. I'll give you an example with what happened in hygienes. For example, carcasses of cattle, sheep, goats, and horses. In Greece, we don't eat horses. It's not illegal, but they don't like it. The aerobic colony count should be between 3.5 to 5, and enterobacteriaceae should be 1.5 to 2, and this is the legislation. And for example, minced beef should be between 10 to the 5th, 10 to the 6th. I can guarantee you that in Greece there's not such meat. We start 10 to the 7, which makes the meat much more nice because it's there's some proteolysis there. So anyway, this is the legislation, and if you are going for microbiological analysis, as I mentioned, it takes a long time because you need a lot of media, you need a lot of effort. The results, they are coming after 24 to 48 hours. And at the very end, as I mentioned, we do that in the end of the finished product. In fact, you have only one number. For example, if you have vanilla cream, which is a very nice product in Greece for babies, and you look for listeria, you are taking this 55 number, this is an example, into account in order to say that your cream is safe. So you are based only in one single number, meat, and the bacteriation. So this is problematic. In other words, we are spending a lot of resources to find analytical methods, but at the very end you have only and you take your decision based only in one single number, and this is not very nice. I already mentioned that there is a risk window. We are waiting about 48 hours. And this gives us a lot of problems. The methodology, especially in conventional microbial and chemical analysis, are destructive. That's another problem. It's costly. You have to have some personnel there. And they give you retrospective results. And we found that food safety, and if we found that the food is unsafe, after 48 hours, so sometimes it's very, very bad. But the 2073 law gives us the answer. Already the answer is there. And in Article 3, they are proposing to the industries that if necessary, the food business operators who are responsible for the manufacture of the product shall contact standees in accordance with Annex 2 in order to investigate the compliance with the criteria throughout the shelf life. So this is a kind of solution. Already the mechanism is there. And what is this Annex 2? They give to the industry some hints how to proceed. For example, studies specification for physical-chemical characteristics of the product, pH, water activity, concentration, okay, all these can be used in order to predict the growth or the survival of some pathogens. And you can see here predictive mathematical models established for food in question using critical growth or survival factors for the microorganisms of concern in the product. Now also studies to evaluate the growth or survival of microorganisms of concern that may be present in the product during the shelf life, like listeria. We have decided that listeria is a special organism, special pathogen that we can try to avoid, especially for the sick people. So this is the solutions that are given to this legislation 2073. Now this is an historical progress. On your left, you can see this paper in 1961, how the scientists, they calculate the growth rate of E. coli. Next to it, with the blue, is the application, the implementation of Robertson-Barani equation. For those that are dealing with predictive modeling, is one of the most famous equations. And of course, we can upload the data in an Excel file and we can find that. So this is 30 years difference. Now, there are plenty of softwares available. All of them are free. I just give you two examples. The MicroRisk Lab, which is dominating Asia. This is a Chinese in Chinese and in English version. And the one that that is produced by our university through the Food Guard project. Is just published last year, almost a year. It's called Growth Predictor, a new predictive modeling and quantitative microbial risk assessment tool, produced by Professor Skandamis. And it's free. You can visit in the internet and you can play about the safety of your food and to make different models. I can give you some examples about predicting my food microbiology in the future. In fact, in predictive modeling, we have the primary models. There is a description of microbial population in a certain condition. Secondary models, these are described how primary models parameters respond to environmental changes. For example, we have different packaging or different temperature or different water activity. And tertiary models are related with the softwares that I described there. There is two also approaches related to population-based, when these guys, they are try to predict the population, and some others, they are very deep in, by trying to interpret and to predict the single life, the life of a single cell. So these are the two main schools that are existing in predictive modeling. Let's go now to the next step, where the farm-to-fork strategy is introduced in predictive modeling. However, now, apart from the parameters that I mentioned, they are proposing to include omics. And the last 15 years in Agricultural University of Athens, we have proposed, this is from one paper that we have done with Fadi, we are proposing this approach. We have a process, we put an ID, a QR code, let's say, in every product. Already there is some ID here, more or less. And yeah, it's probably this bar, single bar, but QR code might be better. And we implement omics or fingerprints. And of course, we are using the database and the algorithms. And then the solution is coming because with the instrument that I will show you, you can take the measurements in some seconds. So you have available the algorithms. And then you translate this measurement to microbial accounts, as I will show you later. And then you have the decision in 5-10 minutes. And that's the difference with the approach that I mentioned before with a classical conventional microbiology that takes about 48 hours. And of course, in this way, you can manage better your products. Okay, so we are moving from control to cognition. We have, in conventional control, we have retrospective and distractive of the product in order to get the measurements. In Industry 4, we are using real-time, non-distractive sensors like multispectral or hyperspectral industry, FTIR, and all of these things. And we can also implement these in mass automation. You know, we might have this instrument inside the industry, and in every single sample, we can make we can take pictures, fingerprints of our product. And this is an example how European Food Safety Authority, that was from a conference in 2018 in Athens, predictive modeling, organized by Americans. They give us, this scheme gives you an idea. For example, you have a food sample and you can see the temperature moving. In this case, it's meat and the changes in the pH. You implement metagenomic results, of course, in parallel with classical plate. And then you are fitting your data and you are create database and models. At the same time, you have temperatures, and these, the metagenomics and the plate counter agar results, they give you a better idea of survival or growth of your spoilage or pathogenic bacteria. So that's the concept, to introduce omics. Another idea about omics is that we are using spectroscopic objectives. This is a more recent paper. And you can see how the analysis, geographical origin, then we can, in this way, we can include different, many other parameters like geographic origin, composition, processing and storage, authentication, and with all these chemometric approaches, some people they call chemometric, some they call bioinformatics. So anyway, they give us results, and we can deploy different sensors. For example, we can implement, we can use vibrational spectroscopy, hyper or multispectral imaging, and biomimetic sensors. All of these, they are actually give us a different idea, a different fingerprint of the food. Surface chemistry is given by multispectral imaging. Volatile compounds is biomimetric. You smell, you can see the meat. And molecular structure is given by FTIR. So you can understand that you have a lot of data and in real time, because by taking an FTIR and measurement of meat or milk or fish or vegetables is very easy. And these are the size of the sensor that can be used. You can see that is like this, like a mouse or like a mobile phone. So you can carry that in your hand, and you can, of course, use it anytime that you want. And this is an example for our laboratory. The black one here you can see in the middle. It's a sensor. On the top is a fish. The mobile gets the outcome, and the plate is a comparison to see the size of all of this equipment. So you can understand that you can have that in your pocket. And of course, the results sometimes are exciting. Some people, they might think that it's fixed. You know, it's a straight line, 99%. So the measurements can be translated by the help of the bioinformaticians to something that it take a long time for microbial, for the food microbiologist. Not only that, this is a neural networks comparison between observed and predicted total viable counts by using multispectral imaging. And this is in beef fillets. That's a very old experiment that we have done. And this is another approach that we had been able to separate 7 foods: beef, pork, fish, pineapple, rocket, chicken, and spinach, to separate them 100% accurate. And some of you might say, okay, beef, for example, rocket and spinach, they're both vegetables. There's not any way that you cannot distinguish from pork. Yeah, might be true, but this is all these products, they are in different stages, from different batches, from different storage conditions. And not only that, but if you think about the future industry, where there will not be men there will be only robots. What you can do is you can scan, and if this industry produces different products, the robots cannot recognize if it is meat or pork or vegetables. So in this way, we have been able, as I mentioned, with FTIR, to separate, to find some 41 robust wave numbers that they can separate the food. So you can have in your mobile, and the robot can distribute to different lines and to sort immediately. So this is the future. And also, if you are a disabled person, and for example, blind, and if you are alone at home and you want to not to eat pork and beef, by scanning that, the computer, your mobile phone, they can say, this is pork, this is vegetable, this is whatever. So if you think about the future, this might be a useful application. And not only about the fingerprints that I mentioned, but also we have very nice instrument doing next generation analysis. And you can see that these are also very, very small. You can carry them. And one other job that study that we have done with Fadi, we discovered that we can actually identify some mid-spoiled gene biomarkers. This is a 10 years ago study, has not been cited, okay. We hope in the future it will be cited more, but this is the first approach to not to use microbial indicators, but instead to use genes that they will tell you that your meat is spoiled, and it's very easy because it takes about half an hour. You can use that even in your restaurant. And this is another recent work that we had mixed now. We have fused, we have make fusion of different data, like conventional microbiology, where most of you know that is counts from the Petri dish, metagenomics and fingerprints. And all of these, they have been mixed. And the people, the bioinformaticians, they give us a very nice conclusions that from one method, one measurement, we can extract decision, we can make a decision, we can extract very useful information. So I think that this is one of the very difficult studies have been done. Because we are mixing different measurements from different instruments. And this is related with muscles. So you can see that we have a very good correlation between pathogens and bacteria species, correlation for the bacteria species identified as spoilers, and correlation with other bacteria species. And what really happening nowadays, because it's increased, that's a field that is increased again and again. This is an example for another project that I coordinate. That was a Chinese-European project. And we have the story, the trajectory of the corn. The corn was on the field, different stages of this maize, corn, and we collect data. So you can see that in every single step we have a tremendous amount of data. So in a way, we are living in an era that we have an explosion of data on chain. For example, on the farm, in the food process, in the logistics steps, we have an explosion of data off-chain about the safety, the measurement, the metagenomics, as I mentioned before, process analytical technologies inside the industry, for food, either for food safety data collection or for food certifications. So we are full now of data. I remind you, before we have only one number and we take decisions. Now we are living in an era that we have plenty of data, and probably this, at least me, I'm strangled because I feel all the tons of data coming on my shoulders and I cannot stand. So we have to develop this that they call data management. We have to develop some models. And before that, we have to find some way to understand what is this data, to upload this data on the platforms. And this is very, very difficult. I don't know, but I'm not a bioinformatician, but one of the most difficult issues that I have to address through the project is how we will communicate from food microbiology to bioinformatics to people that they take the measurements with simple instruments like FTIR. They call ontology. They introduce to me terms that I will show you later on. So what really happened is already I have shown that before we have a single number Now we have plenty of data that are dominated and from those data, we have to make decisions. And I'm wondering, as a simple person, what was easier for me? If I was, let's say, authority, would it be better to based on one single number or to all these data that we are creating? So this is a dilemma. And as a microbiologist, I have to introduce myself to words that I was not aware. Data acquisition, data analysis, data curation. I thought that we are in a hospital. Data curation, you know, somebody to curate the data. How? Data storage. The first time that I was listening to this, I thought that I have to find a warehouse to put the data there. They explained that this is not the case. And data usage. So we are transforming ourselves. So for scientists that are dealing with simple microbiological methods, counts. We have the plates, we count, we are happy, we go home, all right? But now we have to learn all these terminologies. And let's move to the last part. So this we are going to introduce now to Industry 5, which is human centricity, smart factories. And we have to go from Industry 4 to Industry 5. And as I mentioned, it should be human-centric. We have to increase to be sure about the sustainability, personalized nutrition, and all of these things. So we have the meta food industry aligned in food industry fight with human spirit. So far, we are excited about the FTIR with multispectral imaging, with next generation sequencing, NGC. For me, it's next generation student. The same problem. We have to teach with the next generation sequencing, the next generation students. We have to move in this way. And in Industry 5, we have to predict and cognitive meta-food simulation, domain-specific intelligence and cognition, and ethical collaborators and validators to include human there. You know, that's our main concern these days. And of course, we have the ultimate synthesis, the digital twin. Everybody, I think, that knows that expression. So I show you before the pilot with corn. This is a more general. We have different physical assets. We are monitor weather with drones, carbon dioxide, sensors, FTIR, spectroscopic in silos for corn. And then we have the digital bridge, continuous Internet of Things data pipeline stream downwards. And the digital twin is a virtual replica of entire life cycle of the product. In fact, this digital twin is working like a mirror, virtual mirror. Simulated the supply chain in silico by integrated real-time sensors from different stages of the production of the food. And we will be able to predict spoilage. For example, in silos with corn, depending on the temperature and the humidity inside, we can predict if we are going to have some mycotoxin production. So this mycotoxin will go to beef, they will go to milk, they will go to humans. So this is the digitalization of and the mirror implementation of these digital twins. And of course, some people, they criticize always. We have people that they criticize, and they are very good on that. And we need them. We need them because they bring forward problems that we have not identified before. And this is a very nice IEA word, the hallucination threat. You can find only in AI, which means that they give you an illusion about more or less what are you doing. So, and that means that should we be careful about the outcomes of the digital twin? The transparency deficit is also it's a problem. We are using large language models that operate as a black boxes. Scientists like Hawke, they solve the problem of black hole. We have to solve the problem of the black boxes. And the fragility of the prompts, models exhibit a bright reasoning. Minor phrasing you have seen, like the Madeo, we have in ancient Greek an oracle on. So you go there, and depends what the priest would like to say. They give you the answer that you usually want. So is it working like that? So anyway, I will leave to Fadi to explain to you a platform that we have developed through these projects. It's called SurfML. And I would like to also to tell you about this guy. He's a guru. His name is Barabasi. He's a Hungarian mathematician. He lives in United States, and they have used AI to predict the degree of food processing. And you see on the top of this graph, that is what you can do manually with your eyes, manually. But using the AI, almost all the food that they are treat, they found that it was processing. So I don't know if it is good or bad, that, because if you think, probably after that, you cannot eat anything. So anyway, and the engine of cognition, the Chinese, they have produced this food chat GPT. Everybody's using chat GPT, but actually they are Japanese, but they are in Purdue University in the United States. But we are dominated by Chinese, I will show you. So we are moving beyond generic large languages model, and food GPT captures the precise numerical limits, laboratory methodologies, and strict compliance rules required for food for safety, critical domain intelligence. And this is actually their paper, is Ma et al. 2014. And they give you an idea of how these models, they can work. And they are based on the incorporation knowledge graphs to significantly boost the model's capacity to generate accurate and dependable outputs. So this is a graphical presentation of what they have done. It's only recently. So we are not obliged, but we are moving in this direction. At the same time, however, there are some restrictions. Some, as I mentioned before, we don't know if we can use it, how to use it correctly. And this has been identified by the European Food Safety Authority. This gap, I mean, the legislative gap. And we face some problems with the food guard project that I mentioned. We have a lot of new knowledge produced by protective cultures, AI, whatever, and we are address these issues to European Food Safety Authority, but they do not have the solution so far. But I will give you what European Food Safety Authority tried the last couple of years to manage about this gap. And they have created a concept paper on the future scientific data in EFSA. This is 2023, I think. And they have a very nice expression that I would like to repeat is, from data collection to data connection. I mentioned before that we have an enormous amount. Everybody is producing data. So we do have to find a way that to connect this data with food safety, for example, with food quality, okay? And this is our priority. Also, EFSA is looking to transforming big data into scientific evidence. This is very, very important. The second strategic objective of this European Food Safety Authorities will allow European Food Safety Authorities to be prepared with methodologies, data, and expertise indeed for each future risk assessment and communication activities. You can see that there is an agony actually for European Food Authority that they do not have these tools so far. So they are struggling and they are trying to find the correct process. For example, they said, okay, integrate bioinformatics and chemoinformatics approaches, technologies, and data into next generation risk assessment. Everybody is talking about risk assessment. Then we have an increase of jobs that I'm a risk assessor. I'm a risk assessor. Okay, what? How? Of ideas, analysis, and evolution of data project as part of innovation community, for example, academia, stakeholders, modeling. This is the key actions, but I just choose one of them, which for me it's very important. So if you, this is from a scientific journal, Foods is from EDPI. Some of them, some of us, we do not have very respect for this kind of papers, but you can see that China and USA is on the top. Here, sometime after Iran, you can see in Greece, of course, France is well ahead. And if you don't trust this MDPI, I have done a search in ChatGPT before I came here, so I produced this figure. So more or less, they show to us the same, that China and USA are dominant, and we have UK, Netherlands, France, and Germany, and somewhere very close there is Greece, good for us, and the evolution of, that's a conclusion, what I have said so far. It's the evolution of meta-food industry from lab results to both humanization. Let's say that we have phase one, which is conventional control and automation. They give us retrospective results, and we try to have them in real time. The blockchain backbone, it's something that is introduced, the digital twins, and now the second phase that we are going, it's the both humanization, the Internet of Foods. This is something that we have invented as terminology. It does not exist. I'm responsible for that. You know, probably it's wrong, but I would like to introduce this word, Internet of Things, of Foods, sorry. What means that the food inside your refrigerator, already there are some refrigerators that you can control the temperature far away. You can, for example, you can make a lot of assessment with your refrigerators, but you can think that if you have this bottle of milk and this communicate with your refrigerator about the quality, they can tell you later on, okay, we are here, you know, you have to drink me. Today I have only one day shelf life, so be careful. Okay, that's all. Thank you very much.
Thank you very much, Professor. So do you have any questions now for the Professor Nychas, here in the room or in the networks? No, in the networks, not in the room. Let's continue. Sébastien Destercke?
Yeah, so thanks a lot for the presentation. And since you deal with very complete applications, I was curious about the balance between understanding the problem and collecting the right data and finding the right model to perform the predictions you want. So in my mind, it's the first is often more than 90% of the time, and the last one is 10% of the time if you have the right vectors. Would you agree with that, or is it changed?
Yeah, no, I agree. Actually, I guess that Fadi is going to give you some ideas about how he collect the data and how he make the models. And of course, there is should be a kind of interaction. We talk a lot. He's talking a lot with me, unfortunately for him. He's talking a lot with my students. And this is not an easy approach, right? So we have to be together. We have to understand each other. That's the main conclusion that I have drawn all these years, that there is nobody which is the God, let's say, and he's going to dominate over the other. If we don't come together, if we don't get married together, it's not going to happen anything. Some results, some algorithms, they are stupid, they don't have anything. And you understand, it's black box, as I mentioned, okay? But some of them, they are useful because you repeat the experiment. One of the questions that I face from the industry, usually they ask me how many samples, which is a stupid question for me, but I don't tell them, okay? But the issue is that the more data, the more analysis you do.
Please use le micro, dans le micro. Please.
Sorry. The more data that you have, the more analysis that you are doing, with conventional microbiology, the better for the model that you have to create, okay? So the answer to the question is, if you, do I need 100 samples? No, you need 10,000, 20,000, 30,000. As long as you feed your system, the variability of these systems they will create, they will give you options about a better model, they will correct the model, and it's going like that. I don't know if I answered your question because it was, let's say, more on the computer science and okay, thank you.
Oh, it's okay. Thank you very much, Professor. And thank you, Sébastien Destercke, for your question. Let's continue so with Fadi. Well, you can applaud. Yes, thank you very much. Our great speaker. It was very interesting and an exhaustive speak. So Fadi Mohareb, our professor of Genie Enzymatic and Cellular, GEC, laboratory in UTC, CNRS. Welcome, Fadi. So you will talk about beyond prediction, real-time AI transforming food quality, safety, and authentication. Fadi Mohareb has an extensive technical expertise across food science, genomics, and genetics, food quality too, and safety. And of course, advanced AI methodology. Let's go.
Thank you very much, Kaltoum, and thanks everybody for making it here today. So I'm very excited, perhaps a little bit nervous to follow after George on this presentation, what we decided on doing, because as he mentioned, we talk together quite a lot, almost constantly. And it's very, very important because I know not so much or very little on food science, because that's not my background. I'm a bioinformatician. Basically what we decided to do is to divide our talk into a kind of a double act between us. So I'm going to focus my talk about the application of AI in food, some very specific application, because for the same reason that Claire and Sébastien mentioned before, what we would like really as an output from this meeting is to get together with you guys, representative of the research, representative of the industry. And the best way to do that is to give you some showcases of the type of work that we have been doing. And the idea is I'm going to highlight that, as George already pointed out, AI is not really something new or something that was just introduced a couple of years ago. No, actually, we've been doing that, maybe not in the same stream, but it was more focused on machine learning and pattern recognition. But now, thanks to the outbursts that we have in large language models, I'm going to give you some examples about how that can be applied in practice. So I'm going to give an example of using AI in identifying food freshness, identifying adulteration, and combining sensors together, maybe using AI in food formulation, how we can optimize a certain formulation of food, how can we optimize not only, let's say, the recipe of the food, but also optimize the bioactives in that food, and how we could combine all of that with blockchain technology. So food AI, where are we now? You've seen that figure from the previous presentation. Basically, the ultimate goal that we want to do is to move away from the traditional, the conventional microbiology. Sorry, George, but basically to use those rapid and non-invasive sensors that can take the measurement very, very quickly, hopefully in a rapid, non-invasive manner, so that we can streamline it within our production, online or at line, throughout the production chain. Send that result to a cloud where my validated model sits, and that model will send back to the device an answer. The answer can be safe, unsafe, can be fresh, unfresh. That's basically what we've been trying to do for the past 20 years. And in order to do so, basically, our approach has always been, okay, let's first identify those rapid and non-invasive sensors. So we use things like cameras, multispectral, hyperspectral cameras. We use things like electronic noses, because when you talk about food quality or food freshness, it's a very subjective matter. That's basically what I learned from the food scientist. It's what you do when you normally go and buy food from your supermarket or from a normal market or a butcher or something like that. First thing you do is that you check how it looks, and then you might smell it. Or if you're buying some fruits or some tomatoes, you might check the texture. And what we're trying to do with those technology is to mimic the human perception of food. So we use things like cameras, we use things like electronic noses, and we compare them to the expensive laboratory equipment and see how they perform in comparison to these. And that will basically allow us to use the non-destructive approach to send the result, to collect the result in seconds or in minutes, to send the results to a mathematical model, because all these techniques, they generate a huge amount of data. So it's a huge matrix. So if we talk about a technology like Raman spectroscopy, your data matrix in computer science perspective, you will have a dimension of maybe 10,000 or 15,000 matrix size. So thousands and thousands of columns of wavelength. And then on the x-axis, you have your samples. So what we do is that we try to approach that problem of how can I train the model then? Because it's a huge amount of data. So we try to collect data, or to collect data from samples stored under different temperature for different time intervals. So let's say you have a piece of meat, then you divide it into samples, and you store your samples under 5 degrees, under 7, under 10, under 15, under 12, and then you try to sample from them every 3 hours. And you're trying to mimic all the situation as the product perishes, as it gone from fresh to spoiled. And that's basically the data that we use to train our models. So it's basic machine learning approach here. So we collect lots and lots of samples. So you can imagine that the samples are in the rows, and then the spectra, the wavelength are in the column, and then we divide our data into training and testing. We train our model, and then we use the testing to validate the performance. And at the very end, you get a result telling you, okay, out of your samples, your model performed 90% of the time correctly. It can accurately predict the freshness profile of your product. And George highlighted very much the amount of data that you need to be collecting. And usually that is an effort that taking multiple years in the process in order to have that model that you can trust in your food production, that can give you an accurate presentation or representation of the freshness profile or the safety profile of your food. So I picked a few examples of that. That one is also from more than 10 years ago. That basically was the first starting point for us to test how that worked in practice. So we started with a technology called electronic nose. It's a device that is basically mimic the human nose. It sniffs the supernatant of the product. And what we're trying to do here is basically to build that model that can predict the freshness of a beef product based on that volatile profile of the product. So without going into too much boring details about the machine learning side of things, so as always, you divide your data into training and testing. And in that particular example, we decided, okay, let's move one step forward. Instead of building a single model, wouldn't it be nice, or wouldn't it be better if I generate an ensemble, a committee of models that work in tandem, and hopefully, because I'm not relying on a single training process, the combination, the ensemble of that model will give me a better answer than a single one. And that's basically what we did. Usually you run into the problem because, and it's very common nowadays, especially if we want to integrate that, as I'm going to talk about later on, integrated with large language model, you have a committee of models. So how can you aggregate the votes from these multiple models into a single answer? Because the food authority, as we heard, they pretty much like to hear a single number rather than an output from multiple models. So you've got different approaches. You can basically use a majority voting. So if you have 100 models and 90 of them are telling you your sample is unsafe, then you go with the majority. But the majority doesn't always work in an accurate manner. And there are ways around it. For example, you can assign more weights to certain models, because from previous experience or during the training, you realize or you notice that those models tend to perform better than the others. So you give them more weights, and there is quite a lot of work that you do in terms of fine-tuning the different weights between different models until you arrive to a final answer. So from this work, what we've done a series of models. One of them is to predict something called a sensory score. And the sensory score is basically the score given to the product by a trained panel of experts. So you take their answers, take the answers from the model, and you compare the two, because you want to train the model to basically predict that sensory profile. And as we go along and kept adding the models, we realized we started with 200 models within our ensemble, but we didn't know if that's a good number. Of course, the more models you add within your ensemble, the more computationally expensive it becomes. So we wanted to realize, okay, where is the cutoff point? And the cutoff point is basically when the performance kind of plateau. So here we managed to get a performance of 80% accuracy at around 50 models. So that already is telling us, okay, within your ensemble, if you start with 1 or 2 models, your accuracy of prediction is somewhere around the 70s, but then you don't actually need more than 50 models to reach the optimum accuracy. And we've done that as well to predict other things, to predict the total variable count, the number that we heard the food authorities usually asking the industry for. So that's where the paper is. So that was from, I think, around 15 years ago, the kind of our early attempts to use AI in predicting freshness. Another example that we have is to predict adulteration. I quite like this example. It's also from around 10 years ago, together with George. And we had this idea. I don't know if you remember, about 15 years ago, there was something called the horse meat scandal in the UK, where they discovered that in large supermarket called Tesco's, that the beef burgers were actually adulterated with horse meat. And then they realized, no, it's not adulterated with horse meat. It was horse meat with some traces of beef. So it was a very, very big scandal within the UK. Actually, horse meat is edible, and in some countries, if you go to Austria, it's considered like a delicacy, but it's breaking that consumer trust. And that's very, very important. And it has a huge financial and economical consequences on the industry. It takes long time to repair. So what we thought about doing is the general idea when it comes to adulteration is using molecular techniques. So using molecular technology to identify the fingerprint, where is the origin of that meat is coming from. And it's very accurate, it's the gold standard, but the problem with it, it's usually done retrospectively. It's not done in real time, and it takes, you do the test usually after the problem has been reported. So we wanted to use cameras, and the question was, can I, by taking an image of that minced beef, identify if it's pure beef or it has been adulterated? So in our example, we couldn't get hold of horse meat because of that scandal. So we decided to mimic the adulteration of beef with pork. So we set two experiments here. The first experiment, the first goal was, can I use the camera in tandem with machine learning methods to identify if there exists adulteration? And the second experiment was going a little bit step forward and saying, can I actually quantify the level of adulteration? So we use those machine learning techniques, partial least square, support vector machine, and random forest. I'm not going to bore you with all of that. But basically, the take-home message here, yes, for the first experiment of identifying adulteration, as you would expect, the expensive techniques like GCMS has 100% accuracy. But when it comes to multispectral imaging, this is VM, stands for videometer. It's a multispectral imaging camera. It's a small device. It's portable or semi-portable, about that big. And it can be implemented online because it's non-invasive. So you implement it through the production chain, and it takes snapshot images as the product passes. Doesn't cost much, less than 100,000 euros, that's for sure, about 60,000, I think, 50 now. Okay, so, but it has a 94% prediction accuracy. That means I can identify adulteration at a 94% without reverting to the expensive molecular methods. Actually, before going back, experiment number 2 to quantify the level of the adulteration, in fact, the cameras outperform the GCMS, the very expensive laboratory technique, in terms of identifying within a 10% range, not only if my meat has been adulterated, but the level of pork or the level of horse meat in that product. And then about 5 years ago, we started moving into another approach, which is basically, is one sensor enough? Wouldn't it be nice if I combine more than one reading from more than one sensor? Would I be able to push the boundary a little bit and have a more predictive power in terms of identifying freshness or identifying adulteration? So we try to answer this question here. Now we identify that the best performing techniques were the spectral techniques. They're fast, they're cheap, they're portable, and they work quite well in tandem with AI. So what we are trying to do is basically to identify chicken and beef spoilage, and we did a comparative analysis. Okay, I built one model for each sensor, or I use multiple sensors to work in parallel together. And that's basically what we were trying to do. So we compared the single model performance. In that example, it was partially square regression model. And we compared the result from a single linear model or within concatenating a matrix of the output from multiple sensors that are put in tandem. And that was published 2004, not so long ago, about one and a half years. And basically, we compared the performance. The lines in blue are basically the root mean square of error. The higher you want that line to be as close to zero as possible, or that dot to be as close to zero as possible. And the lines that you see in blue are the models working independently. But then the ones in green and in purple are different approaches to fuse the output coming from these models together. And as you can see, throughout the storage condition of the product, whether it's aerobic condition or stored under vacuum or a model that predicts regardless of the storage condition, they always, the sensor fusion approach pretty much always outperform a sensor moving on its own. So that was very important for us to move to the next step. Okay, we have identified, we have shortlisted the analytical techniques that have the potential to work in real time. And those are the spectral, the multispectrum. But now we are moving one step forward and combining different sensors to work together. And as George mentioned, it's very important now as a second step, I hope the video would work, is to automate that process, because our ultimate goal is to make those models available somewhere on the cloud. And if you modify the hardware of your sensor, so instead of sending those spectral data to the computer connected to it, it can send it over the internet where my model is sitting. Then the model can communicate back to the device pretty much in real time. So the first step, as we had, is the data storage and data curation. So we built that platform that basically accept those experimental data, those analytical data coming from multiple platforms. And as you would normally do, you might do some multivariate analysis in the beginning just to check the suitability of your data. So here I'm coloring the samples by their bacterial count. So the higher the bacterial count, the more red it becomes. And at first instance, I can see that the model, I can have a pretty much good model, because I can pretty much draw a line between the green dots, which are the fresh samples, and the yellow or the red dots, which are the spoiled samples. But that's not enough. Usually when I work with food scientists, they don't really care so much about what machine learning algorithm they should use. So we try to optimize and automate that process as well. So using that platform, you can create, deploy, and train your models, and you run them on the server. And the server will do a grid search to identify which combination of machine learning algorithm and which analytical platform works better. So as a food industry, let's say you're working in a yogurt industry, as we will hear later on about the dairy product. Mostly I care about things like lactic acid bacteria, I think. I'm not a food scientist. So in that case, you identify which analytical platform would work best to predict lactic acid bacteria. Might be a different platform combination with a different machine learning algorithm if you're looking at something like Pseudomonas. So the server would work in that manner and will give you an analysis report. Basically, that heat map will show you the best performing model or the best performing model combination. So that was our next step, is to make our models available for the community to use. And then I'm going to give you another example, which is at the other end, and it's basically a work that I've done with my now colleagues. Back then, they were collaborators at UTC before I came here, is about using AI into optimizing food formulation, since the title of our meeting here today. So now with the existence of large language model, what I want to do is, and we do that quite, at least me, because I'm not a very good cook, to find a perfect recipe. So I start with some ingredients, and then I go to my trusted large language model or ChatGPT, and then, hey, can you give me a recipe for a nice pizza or a nice Greek salad? And that will basically, the ultimate goal here is to make me an expert in optimizing my recipe. But that's not what we wanted to do here. What we wanted to do is basically to optimize the bioavailability of bioactive compounds in food. So that work was done by a PhD student of mine that was in collaboration with Claire Rossi and Miriam Kubo between our two universities. And what we wanted to do is, starting from the hypothesis, when you buy a food product, you read the ingredients and you might say, okay, an orange juice, freshly pressed orange juice, will give you 100% or 130% of your vitamin C daily requirement. And because of my pharmaceutical background, I know that vitamin C is an unstable by nature antioxidant. It's sensible to light. It's sensible to treatment. So how much can you trust that label? And that's an image from the Intermarché supermarket. I took it last night or the night before from orange juice. So I like orange juice. You see them on display here. And long and behold, they are in a clear bottle, because clear bottles, they sell better. But clear bottles are exposed to the light. So how much of that vitamin C exists in a bottle? Actually, after, I think, 5 to 6 days, you lose about 30% of the vitamin C because it's photosensitive. It's even worse when it comes to products that are not refrigerated. So the pasteurized orange juice. So they are in clear bottles and they have been heat treated, even for a few seconds. That product has already lost 50 or 60% of their vitamin content. So what we wanted to do is basically not only to test how we can optimize the bioavailability of a certain compound, but to examine the impact of the food matrix itself. The way the recipe is prepared, how much heat, the nature of the fiber, that will impact the bioavailability of your bioactive compounds. So within this project, we picked two products that are simple to cook, because the student has to collect hundreds and hundreds of samples. So we picked biscuits and custard, because they're very quick to make. And we were trying to identify the bioavailability of a bioactive compound called curcumin. And we wanted to see the impact of using different types of fiber on the bioavailability of that compound. So what we wanted to do here, and quite a lot of people are talking about the large language model, and yeah, that's fine. But if you combine the large language model with an actual database about the impact of the food matrix and the food formulation, you will get much better result, and you can combine that with the machine learning models. So in the last few years, AI has been mainstreamed, but it doesn't mean that it didn't exist before. But thanks to the recent advances, now we can make more intelligent model or a model that is capable of providing more intelligent answers here. And basically, the results here are, as you can see, there is a big gap, big difference in the bioavailability, depending on the product, depending on the formulation of the product between biscuits and custard. But then also the impact of the fiber that you incorporate within your product plays a major role in the bioavailability. So the ultimate goal here was, how can I, as a food industry or a, don't know how it's called, the food formulation expert, choose the best set of ingredients, the best food matrix, in order to ensure that what I write to the consumer on the label is actually true. They will reach their body. So the final example that I will give you is about blockchain. So the previous presentation, Joe spoke about the digital twin. And I'm only going to pick one component of the digital twin. As you heard since this morning, when it comes to food quality and safety, two major metrics, they play pretty much the entire role, is what's the temperature that you keep your food on? The higher the temperature, the more the bacteria will strive, obviously, and the faster it will spoil. And for how many times, how much time, how many hours? So blockchain, in simple terms, is basically a way of digital ledgering of things, of, call it, assets. So you can think of it, the closest example that I can think of is when you use something like Dropbox or track changes within a Word document. And it's basically decentralizing that idea of keeping track of the transaction in a system. So rather than having your central bank that is keeping that ledgering system, no, the ledgering system is distributed across all the users. So if you use something like Google Clouds, for example, I share a folder with you. That means that all the files in the folder, if I change my file, your copy will change as well. So all the people sharing that folder will have a copy of those sets of files. So if I lose my laptop in a train, I can retrieve those files from the information coming from, call them, different nodes on the system. And this is very useful because very often in food product, you have the raw material that will make a very, very long journey until it reaches the final product. So moving from the example that George was showing, this is also an example from the same paper that he presented. Let's talk about pizza topping. Let's say salami on my pizza. Wouldn't it be nice, and wouldn't my model be very much more accurate if I can track the entire history for my salami topping on my pizza all the way back till it was a pig running happily in a farm? So the idea here is that you collect all the information from that animal, plus all the treatments, if they have been infected, if they have all their vaccination. And then the digital ledgering system, blockchain, is very good because it's immutable. So once I have set a transaction on the system, it cannot change later on because the other nodes wouldn't agree with it. And that's why it's used on something like Bitcoin. So you do a transaction, the Bitcoin change hands. Once this is done, then it's immutable. But I can keep the history, backward history, to see where that product has been and for how much time. And that's basically where we are using it. So let's say our animal after slaughter, it was divided into two processing facility. Part of it was sold as a steak, as a loin steak, and part of it was sold as cooked ham. And that cooked ham will then move or change hands from a warehouse to a supermarket up until it reached the consumer. And by sending those transactions, I can keep the geographical location of my product and for how much time and under which temperature it has been stored. And we try to incorporate that within the system. This is basically how it works in practice. So the blockchain system, as a food producer, you will basically go and log your product on the platform. And once you click on your product, you can see the entire history where that product has been. So this is a piece of meat that was produced in the north of Greece, and then, or is that Italy? I can't see from here. Somewhere Mediterranean and warmer. And basically here I can see the condition of its storage. So it's probably too little for you here to see, but it was stored under 4 degrees for how much time. And then it was branched. So part of the animal went to producer number 1, another part went to producer number 2. And I can present that in real time because I can store the geolocation of the product as it travels. And if there is any risk identified within my food chain, I can identify that very early on. I can identify, for example, here, if I look at that temperature, this is a plot from the temperature. From the production, I'm storing it under 4 degrees. Everything is fine. It went up a little bit as I moved the product into my van, because depending on where it sits within the van, the temperature might change. But then at one point, something went bad and the product storage temperature jumped up to 10 degrees. So in that case, I can identify where is the weakest link within my chain straight away. And with that, I finish my examples. I hope I gave you a kind of snapshots about different applications of AI, following up also on the food and the food formulation. So thank you very much.
Thank you very much, Fadi Mohaeb. Thank you for your very concrete and energetic talk. Do we have some question for Fadi Mohaeb now? Yes, please, Claire Rossi.
Cannot be detected by, let's say, experience or expertise of the formulation.
Yeah, that's basically the ultimate goal of what we are doing, and it's not very straightforward. So the idea or the ultimate goal here is, if I collect different and multiple scenarios for the model then can arrive to an accurate representation for a particular scenario that I haven't tested before. So it will learn from the hidden patterns within the data what is driving a higher bioavailability, even in a product that I might have not tested, or a particular formulation I have not tested. So the idea is basically as if our students are training for an exam. So you study for your exam by either studying previous questions or looking at some mock exams, and the real test that you will find is not necessarily the same question that you've seen during your studies. It's a new question that you haven't seen, but you have trained your brain enough to hopefully give the right answer even for a question that you haven't seen before. So the same approach goes when I'm training a mathematical model. I'm trying to include as much scenarios as possible. And that's why we heard, actually, we need thousands of samples. But pragmatically, it's impossible. So we need to start somewhere. We start by few hundreds if the student is good, as it was in our case. And hopefully that is a good starting point. And the more data, the more you expose the model, it gets better with time. It's like your GPS now. It becomes very, very good thanks to all the data sent from different cars. So yes, ultimately, yes.
Thank you. Have you got one other question? Yes, please. can you introduce? Tu veux que je donne le micro? Très bien. Let's introduce.
So Kamal Bou Hassoun, thank you very much, Professor, for your inspiring use cases. I have one question related to the blockchain part.
Yeah.
You mentioned Bitcoin as an example, and I can see a blockchain as a cooperative peer-to-peer network, transactions, and incentives. Is there any insight or maybe use cases in this part about the incentive part? Because you have here multiple partners, and how do you incentive them to use this, and how it can be maybe modelized? Thank you.
That is a 1 million euros now, France question. And it's really spot on, because from our experience, what we realize is some players within that production distribution chain are not really at ease in sharing this information with you, because that means that some of the business critical, they consider that the art of their production. So they're not really at ease with sharing that information. However, when it comes to small players within the production, in fact, what they want to do is to protect the reputation of the product that this family farm is producing. So in order for such system to work, completely agree with you that the biggest challenge is to bring all these people together to agree or to realize that it's actually a good idea to share that piece of information. However, with the right amount of data sovereignty and data security, what we collect from the product is not necessarily a business critical information. So from the Ditech project that George talked about, that's the first time that we introduced this project, this concept of using blockchain, and we tested it across 2 different markets, very different, the European market and the Chinese market. And we started with the small family-owned business producers, because we found that it's much easier to get the buy-in from them. But of course, there is a lot of, I would say it's a culture shift to make those players within the industry come together. And when the real incentive here, back to your question about incentivizing them, is basically the protection of the reputation of their product, because they are already facing quite a lot of challenge from the big multinational mass-produced products. So in our case, we focus on the small players, and it's very easy. If there is an outbreak happening, for example, the farmer can go and say, no, actually, it didn't generate from me, because looking back at the entire trace of my farm, I've got all my vaccination in time. I did a test before it went to the slaughterhouse. Those are the tests, and you can speak to the slaughterhouse because they also have the data on the same system. As a food authority, you can log into such system and trace back where the problem actually occurred. You have the entire history of your product.
Maybe one last question. I've seen, no? So let's have a break now. We'll meet at 11 here, if possible. So we are back. We are back for the fourth AA rendezvous here at the UTC. Thank you, everybody, for being so plenty of attending the talk. And now we will listen to Fanny Tenenhouse Aziza. Please welcome her. We can applaud Fanny Tenenhouse Aziza. Thank you very much. She is Directeur Data and Statistics in CNIL, le Centre National Interprofessionnel de l'Économie Laitière. She has over 20 years of experience in the dairy sector, specializing in data-driven approaches to microbiological and chemical food safety. We can go now, please. Thank you, Fanny.
Thank you. Hello, everybody. Thank you Thank you to the UTC for inviting me to present our work in the French dairy sector. So I'm working for the French Dairy Board called CNIL, Centre National Interprofessionnel de l'Économie Laitière. It's an association that is gathering all the stakeholders of the French dairy sectors, so farmers, dairy farmers, also dairy producers, and stakeholders from the retailing sector. So we contribute to the development of research for the dairy sector to improve products and their safety and quality. So in the dairy sector, just an overview of what is happening at the moment. We have many digital tools that are coming in the different at the different stages of the dairy chain. First, farmers, where we have at least 92% that are of the dairy farmers that are using connected tools, and there is 6.6 tools per farm that are connected. So it's very important, and we have at the moment 20% of the farms that are equipped with a milking robot. We have also an important development of Internet of Things in agriculture. And so I'm not specialist of economics, but you have here impressive figures about what will happen by 2022. And also in the dairy companies, we have this digital transformation with analytical methods that are evolving, as we saw this morning. We have also the development of sensors and data platforms, and also the challenge of recruiting data scientists that will help to analyze all the data that are generated. So I'm talking a lot about data because we have a lot of data in the dairy sector and more generally in the agricultural sector and in the food sector. So they come from many sources: research, operation, environment, sensors. Here you have a cow with a connected collar. That is measuring some physical and chemical information of the cow. And we have also imaging, robotics. On the plants, we have many digital tools generating data for logistics, for example. We have also data on products. All that is written on the packaging is information. That is numerical information. We have also data on sales, on consumption, and some reference that are produced at the national, regional, departmental level. And all this will help us very much for many usages to understand what is happening scientifically, to optimize, to trace, to inform. And we had many examples this morning with my colleagues. So these data are used by many stakeholders, of course, professionals of the sector, but also by researchers, public authorities, counselors that goes on the farm, and other actors such as veterinaries, and there are many, many examples. Now, with all this data, we have many important promises of artificial intelligence for the dairy value chain, but generally for agriculture and also the food sector. First, what we can observe in the scientific literature is food safety. And I'm here to talk about food safety. But you have also all these subjects that are addressed by AI. And today, some initiatives are being developed for animal welfare, production, reducing environmental impact, improving milk quality, and also optimizing logistic and distribution related to energy. For example, as Fadi said also this morning, traceability and transparency for consumers is also a promise of AI, and precision, nutrition precision, and also this AI is also seen as a way of making the profession of the sector attractive. So we have to look at that. Just a few words to say that there are a very recent publication of the FAO in 2025 about the future landscape of new food sources and production systems. And they explored many technologies of the future and say for each what will be the impact and the feasibility, and what will be the impact and the feasibility. And it is concluded in this report that AI will be a technological breakthrough. So once again, we have to look at that. So AI, what is it really? If we look at it simply, we have some questions, we have some data, we have some model, we have some results. It was before, and now with AI, we still have some data, we still have some questions, models, and results. But the difference is about the computing power, the computing resources, and also the fact that all these models are learning from data themselves. So we have this upgrading of statistical approach. But the philosophy is the same. And we are doing statistics with data generated by the food sector since a long time. For the safety of food and dairy product, we had many examples this morning, and this slide is maybe a synthesis of what have been said this morning. You have this report from the FAO, once again, on artificial intelligence and food safety, and we also have important literature, scientific bibliography with about 200 papers on AI and dairy products and food safety. And what we can conclude for food safety is that the first use of AI could be the improvement of the speed, the reliability, and the cost of analysis. So it was shown with spectral data, e-noise, biomarkers, all that. We are improving the analytical methods. Also, we have this improvement of enhancing risk assessment. Risk assessment is a methodology to assess quantitatively the risk for a consumer to become ill. I'm eating, for example, a yogurt. What is my probability to become ill? And this can be calculated with inputs. And we can enhance all the risk assessment that were done worldwide with data now from the climate change, for example, or also from omics data, where we can specify some behavior of specific species inside for Listeria monocytogenes, for example. So this is what can be done according to the literature. We also have the possibility to improve real-time process control by monitoring all the data that are generated daily, even minutes by minutes. They can be used to detect weak signals or process deviation during process making food. And finally, authorities are very interested in better anticipating and monitoring foodborne outbreaks with data from notification of alerts at the, for example, European level, but not only in Canada, they are also working on that. So we have many initiatives in the different country in the world that is looking at AI and how it could improve food safety. So many research projects, many tools. Here, for example, you have a tool, TraceMap, that have been launched by the European Commission just a few days ago, I think on Wednesday. And it's about using better the data from the rapid alert system for food and feed, and better trace the batch that could be contaminated, and to find them back. So it's a new tool, and it's based on AI, as they said. And you have here some other initiative in France from Santé Publique France. Here you have something, I think it's in, can see, sorry, China or India, I don't remember. And also in Germany, they are very, very aware of what could be do with AI for food safety. The BFR is the national German agency. In France, I think, but I'm talking under the control of Georges Nychas, we have 3 main European research projects on AI and food safety. The Ambrosia project is about climate change. The Food Digit project is about is a computational food science center and how to move from traditional tools to AI-based tool. And the Fair Omics is about how better use the omics data that are generated with these new techniques. Of course, as everybody knows, there are many key challenges with AI, and so we always say them, but we need to say them again and again about trust, and you talked about black box this morning, explainability, return on investment, interoperability of the system, data lock-in, skills and adoption of all these tools, and also data governance, which is a very, very important subject for us. And all this is described in this report of the European Commission that work on all this limitation of the use of AI in agriculture. In France, we, especially in the dairy sector, we have worked on a practical guide to help all the stakeholders of the sector, first farmers and dairy companies, but also all the partners that are working with these main actors. A practical guide to strengthen trust in data sharing between stakeholders and establish a common framework. It talks about the vocabulary, also the regulatory framework that is evolutive at the moment. There is the GPDR, but also now the Data Act, the Data Governance Act, AI Act is arriving. So we are trying to clarify all this framework and what are the rules for data access, use, and sharing, because this is the base to, for them to be used in the different tools that were presented. So for dairy products, we have been working since about 20 years now on developing a risk-based approach to offer service to dairy manufacturers to help managing the safety and quality of dairy products. And regarding first Listeria monocytogenes, which is a pathogen bacteria very well known, but also other hazards like pathogenic Escherichia coli or Salmonella, of course, and also quality hygienic indicators. Sorry. So the partners were Actalia, which is the technical institute in France. We are working in the network Simprevious. We are working with the RMT Kalima. Also at the international level with the International Committee on Predictive Modeling in Food, which was a very important resource for our research project. What do we have for dairy products in terms of food safety? We have, of course, good hygiene practice that have to be respected and very well implemented at the farm, at the plant, at the retailer. But also we have microbial analysis that helps checking if everything is okay for hygienic indicators, but also for pathogen. We have to analyze product and see if they can be put on the market or not. And this is an important challenge, all this microbial analysis. How many analyses should I do? 5, 10, 30? How much grams should I analyze? 25 grams, 55 grams? So there are many questions around this subject of sampling. And analyses are done at every level of the food chain, at the farm, at the plant, and later again. So you have to define a strategy with the first objective of protecting the consumer, but also you need to rationalize analytical cost. So it's a real question. And this is what we have worked on for many years. With these results, we can address many questions. Of course, is my batch contaminated or not? And we can see that the result is not it takes the form of a probability, so that's it. And we can also work on assessing trends on raw milk contamination, on product contamination, also measuring if control measures, for example, the milk is sorted in function, depending on the threshold of the bacteria Escherichia coli, and should I take off the milk with a level above 30 bacteria per ml or 20? This is a question. I'm losing milk if I do 20, so I have to measure that. And all these results gathered from sampling can help answering that. Also, you can check if maybe there are relationships between the presence of a pathogenic bacteria and also a hygienic indicator. So these data are also useful for that. And at the cheese process level, you will have questions such as the impact of a raw milk contamination, a recontamination, a cross-contamination on the final product level of contamination, and is it a risk for the consumer? You can also work on the shelf life of the product. Should it be 15 days or 18 days? You can make calculation for that with predictive microbiology model. You can optimize sampling plan, and you can verify, of course, if your products respect a specified microbiological criterion. In Europe, we have the specific regulation. So you can answer with many questions with all these results, and this is what we try to do, reusing all these results to answer different kind of questions. And so we developed some tools based on the data and based on model. And our first tool is a tool to help dairy products processor to define their sampling plan. How many samples should I take? How many grams? Above which threshold C should I reject my batch or not? And you have some calculation to make with this tool, and then you can obtain, by doing more or less samples, you have a graphic that will provide you the probability of rejecting a batch, but also the probability of detecting a batch based on some hypothesis. So it's this first tool, and it's also based on former analytical results that were collected before. You can adjust your sampling plan. So this tool has a specific is specific to milk powder, because as you say, infant formula are very sensitive products, and the sampling plan are very important. You need to do many analyses, so you can work on this probability of putting some products on that could be contaminated on the market and reduce it. Then we have a second tool, which is called the Dairy Product Safety Predictor. It allows calculating a risk of illness, and it's based on data from all the food chain, contamination levels in milk, environmental parameters such as temperature, pH, water activity, lactic acid in the products during the production at the different stage, from the milk to the cheese. And so you have the ripening, you have molding, you have acidification, many stages. Also challenge test data, that is to say experimental data where we have inoculated a pathogen in a milk matrix and see how it is behaving, and also consumption data. So with all that, we are able to calculate some risk of illness. But what is interesting is also to evaluate the impact of control measures. We know a level of risk that will be a reference, but if I sort my milk, if I sample the products, if I put this shelf life, if I do pasteurization, what will be the impact on this probability to become ill? So we have an interface where we can make simulation for different type of products, especially cheese, and for different bacteria, and dairy processors can use it. So you have all the different kind of cheese, soft cheese and cooked pressed cheese, blue cheese, and all the major pathogenic bacteria that we can find in foods. So all these models are based on research project, of course, and were published. So you have dedicated publications. And the third tool, as I said at the beginning, is that data can be used to do real-time process control and also monitor contamination level of, for example, hygienic indicators, detect weak signals and deviations, small deviation in the process. So when you put all the results together, you can see, for example, a decrease of contamination, and it provides some information for the about the a good hygiene practice that could have been implemented, and it says that it's okay, you have done well, it's useful. So we have a dedicated tool, it's a data valorization dashboard, where we can see the evolution of contamination levels along time, such as control cards, but we have very specific control cards, air chart for quantitative data, bacteria that can be counted, but also P chart for data that are either conform or non-conform results, yes, no, binary results. And they are very, very specific, following some recommendation from FAO and OMS, yes, OMS. We have also tools that will allow to check if we have some correlation between two germs using former data, and tell you should analyze these germs, for example, Pseudomonas, and if it's above a certain threshold, then the probability that you have a salmonella is high, and so you need to do something. Because salmonella, you have it in very, very low concentration, and you can't find it, so you want to rely on something else to manage this pathogen. So it can do many things. I won't go in details, but it's quite interesting. Now, regarding AI, we are first trying to implement to make all the quality managers use all the tools I have shown, but we are also, of course, looking at what is promised by AI. So we have a research project at the moment, the EMI project, with Maeva Kayat, who is the PhD student, and all the partners that are here. And we are working on the extraction of experimental data, especially the growth of a bacteria in a food product, let's say a fish this time. And the extraction is very hard to do when you do it manually. And AI offers some possibility with LLM to extract automatically and standardized and put the data, the results in the good box. And so we are trying to see if this tool could help us to make our tools for growth behavior, simulation of growth behavior, to implement it with new information, new bacteria, new food, new growth rate, new inactivation rate, new lag time. And so it will go faster with an automatic extraction. So this is what we are looking at the moment. So to conclude, they are data and AI tools for dairy product safety. I would say yes, because we have some tools that are being deployed on the field. with the dairy stakeholders. Authorities are also using it. Agency like ANSES in France, the National French Food Safety Agency, uses, for example, quantitative risk assessment. And so, but it's not so easy to make people use it because you need data scientists, you need people that are interested in mathematical modeling. So this is a hard exercise to make people adopt this kind of tools. But we are making progress at the French level, at the international level also. And regarding AI, it could be a tool, it will be a tool because as it was said, AI will be a technological breakthrough. So, but we are having a strong attention of data governance, data quality, data system interoperability, the fact that we need students that have the skills to use these tools. And so there are many uncertainty on the subject today, even if we are looking at it and working with it, we need to be very careful with the subject of AI and to be part of the movement. So yes, we can put off this, I think. And I want to thank you for your attention.
Thank you. Fanny Tenenhaus, Aziza. Have you got some questions for Fanny? Yes, Sébastien Destercke. Je vais me rapprocher pour te donner le micro afin qu'on entende bien pour les internautes.
Okay. Thanks very much for the talk. It was very nice to see Sim Previous because I had the opportunity when I was at CIRA to be a small part of it, but Patrice Busch was a big part of it. He will be next speaker, I think. But my question is, so you focused on risk, which is definitely something very important, and which one robust assessment. I was wondering if you could say a word whether the CNIL is the CNIL, let's say, has also some involvement in improving process management and food quality. It is once you are sure that the food is safe, you want also to improve its organoleptic qualities or things like that. And I was wondering if you had some activities in that.
Okay. This association, CNIL, is a collective association gathering all the people from the food sector. So we are working on a pre-competitive research project. So safety is a major issue for everybody, and we are working at the national level on this subject. As soon as we touch to quality and organoleptic, we are entering in the maybe competitive sector. So we can work on it, but it's not the major activity in terms of research.
Okay, thank you. Another question? No. So thank you very much, Fanny Tenenhaus Aziza, for this example, very pragmatic at the CNIL. Thank you. You can applaud Fanny, please. Thank you. Thank you very much. So now let's continue with Patrice Busch, as promised, from INRAE, research engineer at INRAE, yes, from the knowledge engineering team, ECO, from Montpellier, about how knowledge engineering and AI support developments in agro-resource processing sectors. We listen to you. Ok, on règle la technique. L'occasion pour moi... to say that his research works mainly concern data and knowledge integration. We've applied projects in food and bio-based product engineering.
Works. Thank you very much for the nice introduction and invitation to make this speech this morning. Then the title of the talk is how knowledge engineering and artificial intelligence support developments in agro-resource processing sectors. And then we'll first begin by the scope of our research. We are concerned by food, bioproducts, and waste engineering in the context of bioeconomy and global agri-food systems. I will make a focus on the bio-resource processing aspects. And in this topic, we have to deal with two research challenges. First, designing food quality, we spoke of that just before, from agriculture production to the impact of diets on health and the environment, but also designing biomass construction, deconstruction processes for the production of bioproducts and the use of waste generated by human activities. I will make a focus on one subfamily of artificial intelligence, which is not very well known, which is called knowledge engineering, because everybody speaks in general of machine learning and deep machine learning, but there are also other families of approaches which may be combined with machine learning, and knowledge engineering is one of them. It is a scientific AI discipline that involves integrating expert knowledge, representation, and reasoning into computer systems to solve complex problems. And I will make a focus on the use of knowledge engineering for decision support system involving qualitative and quantitative information and coupling with machine learning. Knowledge engineering in food and bioproduct engineering is challenging because we have to solve complex research questions which are based on multidisciplinary fields and disciplines. Therefore, we have to deal with heterogeneous experimental data, expert knowledge. Therefore, our research question is how to represent and reason with heterogeneous, incomplete, and uncertain data. Our approach consisting in trying to structure those data and expert knowledge, and the solution we propose is to standardize data and metadata using ontology, and we present on the next slide. Therefore, it is then possible to query and link the data and to share them, in order to share them or to reuse them in recommendation systems or using machine learning for knowledge discovery purposes. And you will see that we are working in an iterative approach, assessing the quality of decision support we propose with experts of a domain and who provide us feedbacks to enrich the knowledge graphs we are building. Therefore, we are using ontology. What are ontologies? There are models which permit to represent complex knowledge using concept and semantic relations linking concept. And there are different ways to do that. Our choice was to design ontology, to use ontological languages standardized at the international level by the W3C. Those languages are whole to define ontology, RDF to create knowledge graphs, conforming to all ontology, and Sparkle to query RDF knowledge graphs. Main benefits are the availability of open source tools implementing those standards, and the possibility to reuse ontology which are recommended by W3C to enhance interoperability. I will show you some examples of that. But now I come to some examples of solutions we have designed based on this knowledge engineering approach for decision support system. In fact, I will make a kind of presentation with a gradual adhesion to this kind of tools. And the first one I will begin with is structuring expert knowledge in order to recommend some technological action. Therefore, I think it must be 15 years ago, people from PDO cheese chains came to us in our research lab in Montpellier because they had a problem of lack of capitalization and transfer tool. They have a problem of loss of knowledge and know-how in the chains, and therefore which were due to important turnover and difficulties in recruiting. And the question they asked was how to explain and recommend a technological action in order to correct a product defect or to obtain the product quality. Therefore, we proposed to them a solution, a generic solution that we could also reuse for other chains. Here I put some pictures about biocomposite design for food packaging. The technological reasoning we have developed for them is structured in the form of a set of decision trees. For each decision tree, you are interested in a given situation of interest, which may be a defect or quality to reach. And therefore, we are going to organize in this decision tree, by means of logical operators, the connection between the defect and intervention levers through candidate explanation situation. Therefore, we also incorporate in the reasoning the explanation situation. Here you have a first example of that. It's a real decision tree coming from one PDO cheese chain. It's the reason why that some analytical values are anonymized. We have a problem of excessive salting, and what you can see is that we have the different explanations provided by the expert of a domain. Here it's written that it is a significant salt intake by the cheese during the production. We have two sub-explanations. First one being that the cheese is conducive to salt intake, and the second one, which is developed here, is that it comes from conditions favoring salt uptake in brine. They are the development of sub-explanation till the recommendation, which is to dilute the brine. And you have in red, you have analytical value, the density to reach, which is represented in the knowledge graph. In fact, in such decision trees, you may have a lot of different possible explanation and technological action recommended. Therefore, the users asked us to make some multi-criteria filtering in order to help them to explore the decision trees. And you can see here what we did. In fact, we gave them the possibility to filter, for instance, of action efficiency. It has been assessed by the expert of a domain. Here, we restrict to only very effective actions. We also have a second criteria, which is used here, is the agreement between experts of a domain on this assessment. It must be here good or average. And you can see that we restrict here to 3 of the 15 possible recommendation for this default. And what we can also provide as we manage a large set of decision trees for a given cheese chain, it must be 100 or more than 100 decision trees with a lot of possible recommendation. Therefore, we provide also the possibility to assess the possible side effect. Therefore, we query. For that, we query in fact the other decision trees to see in which decision tree we use the same lever here, which is the brine time here, and to see if we don't have other defect which may appear, is for instance an unpleasant taste of odor, brown paste, excessive proteolysis, etc. This slide to show you that we have developed a generic solution, therefore we reused it for other chains. Here it's an example from the vegetable powder production chain. We use vegetable powder after that in order to make some biocomposites for food packaging. And here you can see here a decision tree in a graphical representation where the defect is that we have a particle obtained after milling which are too large in comparison to the expected median particle size. And the same as before, you have the possible explanation of that is due to the wrong mill setting, or that the engine consumes too much energy, and we have sub-explanation till the recommendation, which are written on the right part of the slide. Here, this slide to show you, I said that ontology on concept and relationship between concepts, just to show you a real example of that. Here, it's the CAPEX ontological model we have developed to structure the knowledge graph, which is associated with decision tree. You have two parts. The part which permits to explain the situation of interest, and the second one, which permits to define the type of action associated metadata. And you can see that we have concepts which are represented here in blue rectangles, which are linked to other concepts through relationships. Now we can go further. We have expert knowledge, but you also can put into the knowledge graph experimental data, and we can see that here we will be able to make some case-based design support. We are in another, in the first example, we wanted to preserve the existing knowledge. Now what we want to do is to understand, to master the quality of bioresources. It is more dedicated to research and development engineers or scientists. And the question who was asked is how to recommend a technological itinerary in order to obtain a product with a given quality in a repeatable way. And therefore, what we propose here is a kind of iterative approach, as I said in my introduction, based on an open science approach in the community of scientists. Therefore, it is done in 4 steps. The first step, you define the experimental aim, the quality you want to reach. Second, you will consult the knowledge graph in order to retrieve similar data which had been produced in past experimentation. After that, you will inspire from that to reproduce the same XP and enrich with new characterization, which will be stored in the knowledge graph. We have an iterative approach to enrich the knowledge graph. Here is the solution, the ontological solution we have designed for that. It is called the process and observation ontology. It is a generic model in all, the language I presented just before. And here it's an example in which we could reuse already existing ontology recommended by W3C. It is called SOSA and SSN in order to modelize a part of our ontology. Our ontology, in our ontology, we describe processes, itineraries as a sequence of steps in which you have input and output. It is represented here in the simplified representation of the ontology by concepts which are in blue rectangles. They are the original concept we have introduced compared to the literature. And after that, we reused SOSA SSN in order to represent observations with material and methods. And also, it is not written on the slide, but we use also recommendation from IADOPT in order to represent scientific variables which are put in the data tables. Here, in the previous slide, I presented you the core concept. But of course, if you want to annotate a particular experimentation, you need to have a very rich vocabulary, for instance, to define the different components you will use in your process. For that, we decided to reuse the vocabulary which has been proposed by the European Food Safety Agency, which is called FoodX2. And we complemented it because it is only dedicated to food. As we are working in the large aspect of bioeconomy, we also used some other concepts for biomaterials and for the management of waste. Therefore, now we have a thesaurus called Transformon, which specializes the PO2 core concept, which is more than 10,000 concepts, and in which we have EFSA concept plus other one, which has been enriched using LLMs for the definition. We use LLMs in order to provide some definition to all the concepts before we have definition for all the concepts. Now here I come back to my example of reusing data. Here I am in a situation in 2020. We are in open science aspect, therefore we publish our data in data papers, and therefore that's the reason why there are some references here. Here in this data paper, we published experimental data about the production of vegetal powders from different biomasses. Here we are in an itinerary 3, in which we have made some powders from MCore. And you can see that we have a detailed itinerary, first cutting milling, and after that an impact milling to reduce the size of a particle. And you can see that we store in the knowledge graph information about the impact milling. We know the machine which has been used, it is a UPZ. And we know also which are the control parameters which will permit to reproduce the same experimentation several years after. You can see also that we associate to the output component of this impact milling some observation. Here, for instance, we have an observation about the size of a particle, granulometry, and you see that we register the name of the equipment which has been used to do that, and also the parameterization of this equipment, which are here some standard operating conditions, and we have a table of values. Here we know that we have a medium particle size around 150 micrometers, which is called volume D50. And now I come several years after, 4 years after. In fact, the same team was interested in reproducing the same samples in order to enrich the characterization of a powder. Therefore, what they had to do only to query the knowledge base, the knowledge graph, using the Spock tool for simple PO2 query tool. It is a web form in which they have only to select the powder, the biomass they are interested in, here MCore, and then to specify the aim. Here I want to make a powder of 150 microns, and you can see that, of course, they can retrieve the data I presented just before. They can go back to the database using the tool, which give them all the details on how to reproduce the same XP. They did that, and 4 years after, in the next data paper, published in 2024, you can see that there is an experiment, an itinerary 5 about MCore with the same equipment and same control parameters, and they could succeed to reproduce because they obtained a powder of 160 microns. And you can see also that they enrich the knowledge graph with characterization. Here we have, for instance, biochemical composition characterization, which are added for this biomass. Okay, and on this last slide here, I showed you, I come back again to the importance to reuse already existing ontology. On the left part, it is a simplified representation of our core model, but you can see on the right part, a recent version of full representation of PO2 ontology, in which you can see that we only design new concepts which are the blue one, and the other one we reuse from the literature for interoperability purposes. Okay, now we repeat that, and when you have enough data, experimental data, you will be able to go further. To go further, it means that we have enough data to make some machine learning and to make some model-based design support. Okay, therefore it's the same question of our scientists, research engineers, who wants to master the quality of bioresources. Therefore here, the question is how to discover links between qualities of bioresources and functionalities of product you can do using those bioresources. Here I take an example. We did, it is here, the question was to design food packaging composite using polymer and vegetal powders, combining them in extrusions. And the question was, which is the biomass and processing parameters to reduce the cost of PHA production, the polymer production, which is expensive, for a given food pack application. And in fact, we had a numerical modeling lock because at the scale of a sequence of unit operations, there is no deterministic model available. For instance, here we have a sequence with a drying, with an extrusion, with a shaping of therefore it is not possible to reuse already existing model, and the rule of mixture is not applicable in this context. Therefore, what we did, we extracted from the knowledge graph more than 100 experimentation to make some biocomposites from different biomasses. And you can see here on the upper part of the screen, the input variables representing the characteristics of the biomass. Here it's a biochemical composition, and also process parameters like the D50, which is the size of a particle, and the filler content, the quantity of vegetable powder you put into the biocomposite. And therefore, you could see that using here one machine model, which is Bayesian networks, we could establish some connections between the input variables and output one, which are represented here in blue, in which we have some processing parameters like the melting temperature or function mechanical properties of the targeted biocomposite, like the stress at break. And thanks to those machine learning models, we had, of course, tested others, SVM, different kind of machine learning models. We kept the best one for each output variable, and we could be able, like that, to compute an abacus for a combination of input variables. You can see here input variables are represented in green on the left part. On the right part, I only kept 4 example of output variables. We could be able to predict the values of the output variables using the machine learning models. And now here on this abacus, you have some more than 60,000 virtual itineraries which has been computed thanks to those models. And therefore now what is possible to do is to use that in reverse engineering, saying, for instance, I would like to make a biocomposite with a filler content between 35 and 45%. I want also to have a stress at break of a biocomposite which is not so far different from the original PHA, in which I have added some vegetable powder. And you can make some restriction like that, and therefore you will select only the one which are the virtual itineraries which are represented in violet, and it gives you some recommendation on the interval of values for the particle size and also for the biochemical profile of a targeted biomass. And now, if in plus you have a list in your knowledge graph, you have a list of candidate solutions, and we saw that we have that. Therefore, thanks to the fact that all the data are represented using a standardized vocabulary, it will be possible to query the set of knowledge graphs. Here I will query the knowledge graph associated with the data paper of 2024, using as restriction the biochemical profile coming from the abacus, here in terms of linin and glucose rate, and it was possible then to recommend pine bark to produce the targeted biocomposite. Conclusion, just to give you some result, we succeeded in making an innovation with action recommendation tool we have developed, the CAPEX tool, because now 19 PDO cheese chains, which represent more than 70% of the French national production, and all the dairy schools use this tool for 3 years now. Therefore, they have created an association to do it. The case-based design support using the PO2 ontology won the Open Science Prize Award in 2023, delivered by the French Ministry of Research, and the coupling between PO2 modeling and machine learning won also the Best Paper Award in 2021 conference, Metadata and Semantic Research. What next? Our interest is to continue to try to reuse the data put in the knowledge graphs and the machine learning models, and it is what we are doing now using another family of approaches in IA, which is called multi-agent system. Here we are interested in simulating the creation of a biorefinery at the level of a region. Here we are working on the region Grand Reims, and the idea we have a responsibility to develop an agent which modelizes which permits to simulate the introduction of a biocomposite producer at the level of this region. Another aspect of current interest for us is to try to interact, to obtain added values for the interaction of the different knowledge graphs I have presented just before, and also, of course, to introduce a sovereign generative AI, because now people are used to use this kind of tool. Therefore, it's very easy to introduce the content of the knowledge graphs in the generative AI. And also, I wanted to present you the core team of IT engineers of our research institute who participate with me to the development of a software ecosystem I've presented you, and of course our numerous collaborators, scientific collaborators who help us to develop this ecosystem. Thank you very much for your attention.
Thank you, Patrice Buch. Thank you very much. Do you have any question for Patrice Buch from the INRAE? Avez-vous des questions avant d'aller faire la pause déjeuner? Sébastien Destercke, j'arrive. Bon, je te donne le micro pour les internautes également.
Thank you, Patrice. I had two short questions, let's say. How much LLM, in formalizing and structuring ontologies, how much LLM has done your job easier, or are still they not up to the task of providing well-structured, mistake-free ontologies, I would say? And yeah, I was a bit curious about the multi-agent and the way you would deploy it, but I think we can take these second questions to the lunch.
Yeah. LLMs, in fact, we use them as everybody, I will say, before, as I presented just before, we use them, and it was very interesting to associate definition to concept in ontology, because in general, it is not, we have only the list of concepts without the definition. Now with LLMs, it is not more a problem. And the second aspect also is to use it in order to make some software development. For instance, the Sparkle queries, the shackle constraints, things like that. We can generate it more rapidly using LLMs, of course. It is for the moment the kind of application we do, and of course also the generative LLMs we want, the sovereign, because sovereign generative AI we introduce because people are used to do that. Okay, we could try, but for a moment we didn't. It was not an idea we had before. We'll see if it's necessary to do it.
Okay, thank you. No more questions? So thank you for your participation. Merci à tous. It's time to go to lunch, and we'll meet in 1 hour and a half. You can, thanks to Patrice. So we'll meet at 13:30, please. À 13h30, on se retrouve ici même. À tout à l'heure. Merci beaucoup.